Okay, we are going to start off today by talking about exponential models and practical real world ways that these are used. So first we have to remember our parent function so that we can go back to and kind of know how to put things in. So if you'll recall, you have your A of t equals A times 1 plus r to the t for growth, and A times 1 minus r to the t for decay. So this one says in 2015 the population of a small town was 8,000. Now remember, that is our starting rate. So that 8,000 is our A because that's where we started off at. So I'm going to go ahead and put that 8,000 in for our A. And it says the population is increasing. So that means that we're going to be doing the growth model here at a rate of 2.5% per year. Now remember, we have to turn that into a decimal. So we're going to have 1 plus 0.025. Rewrite an exponential growth function to find the monthly growth rate. So for our time, we would usually have 1 year there. But in this case, we're doing it 12 times in a year. So what we're going to do is put 12t there. And the other thing is that this rate that we're doing is, we can't have a 12 out here because that changes the whole thing. So what I need to do is take that rate and we're going to raise it to the 1/12. So we're going to divide that rate into 12s and then take it to the 12t. So that the 1/12, when we multiply the 1/12 by the 12, we're just going to get t, right? So now let's put this in our calculator. So when we do that, I'm going to get 8,000 times 1.00206 to the 12t. Now notice I only put this part into my calculator. Now I didn't pull that up on Desmos. You guys should at this point know how to use that. If not, I can give you a little lesson one-on-one during class. So now in order to solve for t, what we're going to do is we're going to look, well, we're not actually solving for t, we're looking at that monthly growth rate. So the monthly growth rate is just this part that's after the 1. So if we took 1 and subtracted, or if we subtracted 1 from that 1.00206 minus 1, we're going to get the 0.00206, and then we make that into a decimal. So it's 0.206% is the monthly growth rate. And we did that by breaking apart our 1 year into those 12 months. The monthly growth rate is obviously going to be smaller than the annual growth rate because you're doing it just, you're dividing it into 12th, but it's not 1/12 of the growth rate because you have to take into consideration your exponents. All right. Our next example is talking about compound interest. So compound interest is a little bit interesting because if you're adding interest on top of interest, if you did it annually, then you're just getting paid interest once a year. But if you're doing it monthly or quarterly or semi-annually, then that interest is adding up more and more over time because you're doing it more frequently. So this is the compound interest formula, and you need to remember what these letters stand for. So P is how much we invest initially. P stands for principal. R stands for rate. And again, we want to write that as a decimal. N is the number of compounding periods per year. And we'll talk about kind of what that means in just a bit. And then A is the amount in the account after T years. So you've got A, and T is always time in years. So you'll notice that what they've done here is they've divided the rate by the number of times you're compounding, and then you multiply the number of times you're compounding by the number of years. So we're going to do several calculations here for Tamira, and I'm going to try to leave that equation up here where you can see it. So annually, if we look at annually, then our N is just 1 because it's 1 time per year. So we would write that A equals 5,000 times 1 plus 0.04 over 1 to the 1 times 3, because 3 is our number of years. And again, you just put that in your calculator and you get $5,624.32. If we do it semi-annually, semi means by or twice, so half every half year. Because like semicircle is a half a circle, so semi-annually is a half of a year. We're going to have I'm going to put semi-annually here. Our N is going to be 2 in this case. So A is going to be 5,000 because we're still putting in the same amount, plus 0.04, but this time we're dividing it by 2 and to the 2 times 3 because we're doing it twice a year for 3 years. And so that number, when you put it in your calculator, is $5,630.81. Now notice that you're getting more money. It's only $6, but $6 is $6 by having an account that does it semi-annually. So as we go quarterly and monthly, it should get a little bit bigger. So if we do quarterly, then our N is going to be 4 because there are 4 quarters in a year. So it's going to do it 4 times a year. And then we just plug that into that same equation. So 5,000 times 1 plus 0.04 divided by 4 to the 4 times 3. For this one, we get $5,634.13. Now again, that's a $10 difference. So again, we're getting more money. And so our monthly, just like we talked about in the last one, our N is going to be 12. So we're going to do A equals 5,000 times 1 plus 0.04 divided by 12 to the 12 times 3. Now, when we put this in our calculator, we're going to get $5,636.36. So not as big of a difference between these two, which is kind of interesting, but that is something to notice because we're going to have our 4 years. So you definitely want your interest to be compounded more often, because what happens is if you look at your exponents, the exponent here is just 3. Is it going to work for me? The exponent here is 3, but here it's 6, here it's 12, and here it's 36. So the larger that exponent is, the faster that your money is going to grow. All right, on to example 3. Now we're going to talk about something about continuously compounded interest. So this means that every second of every day, the interest is compounding. So when we think of that, it's going to pay, let's say we have $1 in account and we're getting 100% annual interest for 1 year. Now that means that if we just, compounded it 1 time per year, basically our money is going to double. But what if we make more and more periods? So what if it's 10 times per year, or 100 or 1,000 or 10,000 or 100,000? And we're going to see what this looks like what that rate or that amount looks like the more that we to put in. So if we start just with 1, we're going to have 1 plus 1 over 1 to the 1, which is just 2. That was easy. But if we change that compounding period to 10, what we end up with is 2.59374, and on and on and on. If we do it 100 times per year, what does that number look like? Well, it's going to be 2.70481, and then 1,000 times per year. Now, again, I've already done all these calculations in my calculator, which is why I'm able to write these out so quickly. 2.7169. Okay, let's do it to 10,000 times. And that gives us 2.71814. And then if we do it to 100,000, oops, I think I've put too many zeros on that. 100,000, there we go. We're going to get 2.71826. Okay, now if you did it to like 1,000,000, you would actually still get pretty close to this number right here. This number is a special number. Let me see if it's going to let me. There we go. This number right here. This is called the natural base. And what it's saying, it's that continuously compounding interest. And just like you guys know 3.14159, that number as the symbol pi, this number 2.71826 going on forever, and that one goes on forever, we know as the lowercase e. And just like pi, lowercase e is a number on your calculator. It's just a button. You push it and that it automatically fills in that number. Now, these are not exact values. Do we have to go on to exact values? No, because generally we're talking about money. And so we're really only worried about those first 2 decimal places where our cents go. So as we start talking about it in terms of money, we'll be mostly worried about those first 2 decimal places. But when you're calculating, you need to use that E key on your calculator. Okay, so let's fill in this box here. It says the natural base E is defined as the value of this expression, like we talked about before, as x goes to infinity. So that natural base, the 2.7182828,459 is irrational. It doesn't end, but it is the smallest number that you can possibly get when you're compounding 1 continuously. So there is a continuously compounded interest formula where we use this as our rate. And so that is found by A equals P E to the RT. And we just say P A pert is the easiest way to find it. R and T are R times T is the exponent. And in this case, R is our rate. T is still time in years. P is our principal amount. How much we started with. E is that natural base. Button on your calculator. And A is the value after 2 years. And always put the rate in as a decimal. Okay, so now let's look at an example of this. So what I always do is P equals R equals T equals and A equals, and we're going to fill all of this in. So Regina invests $12,600. So that is our principal in an account that earns 3.2 annual interest. So we're going to put that as 0 or 0.032 compounded continuously. What's the value in the account after 12 years? And we're rounding to the nearest dollar. So A is our unknown. That's what we're trying to find. So this is a pretty easy one just to plug into a calculator. So we're going to put 12,600 times E to the 0.032 times 12 years. When you put that in your calculator, you get that A is approximately $18,498.63. So it's a pretty good growth return there. You're getting almost $6,000 for putting your money away for 12 years and not doing anything. You don't have to work. This is the beauty of compound interest. Oh, there should be another 0 there. I wondered why that didn't work. 0.0. So you go 1. No, there shouldn't. It's 0.032. I had that right. 0.032. All right. So A is this. So this is the amount in the account after 6 years. All right. Last example. We're going to use these 2 points to find an exponential model and figure out what we're doing. So let's go back to our original y equals a times b to the x. And we're going to fill all this in. So first, we have to figure out what our growth factor is. So this is obviously increasing. And to do that, we're going to do 1,400 over 1,000. When you simplify that, you get 1.4. So that means our b is 1.4. But we also need to know kind of where we're sitting. Well, we don't know what our initial number of emails are. So what we're going to do is we're going to do 1,400 and set that equal to A times 1.4 to the 7. And the reason we're doing 7, why are we doing 7? Well, 2016 is 7 years after 2009. So we know that our initial X would be 0. And, but we don't know what our initial Y would be. So we have to kind of figure that out. So when we solve for A, we're going to do 14 divided by 1.4 to the 7. And when we do that, we get 1.33. So that means that A, our initial value, was probably 133 emails, which is kind of crazy. But again, we want to keep that as a decimal, so it's not crazy. So then our equation is going to be y equals 1.33 times 1.4 to the x, where x is our time in years. When you have data points that are x values that are 2 units apart, so like this one, it was easy because it was just 1 unit apart. So we just did 14 over 10. If they're 2 units apart, you've got to divide that by 2 because you're looking for a slope more than you're looking for, and our average rate of change here was here. But when you've got 2 units, you've got to divide it by 2 because you're taking that change over 2 years. Or if it were 3 units apart, you'd have to divide by 3 because that change happened over 3 years. So that's kind of how we do that. Now, for example 6, We are not going to do this in here today because I'm going to actually show you, just like we did with our quadratic regressions, how to do a regression with an exponential model in your actual calculator. It's a lot easier than doing it in Desmos. So we'll do a regression together as a class. That'll be the first thing we do when we come into class. So